Another topic needing to be discussed then will be on our learning objectives down here towards the end, how we use Graham's law, another law that relates to gases, in this case to relate the relative rates of effusion, how gases move, how two different gases move, is described by Graham's law. What do we have for another gas law? So first we have to explain what on earth these diffusion and effusion things are. Diffusion is the mixing of gas molecules by random motion under conditions where molecular collisions will occur. And effusion is a little bit different. It is the escape of gas through a pinhole into a vacuum without molecular collisions. Now, you're represented by these two pictorial diagrams. And so there's a diffusion through a space in between two sides of the gas container. One gas starts out on the left, one starts on the right, and they're going back and forth. On the effusion example, the gas is escaping only in one direction through a pinhole into a vacuum, and there are minimal collisions for that reason. We're going to relate these rates of diffusion and effusion using something called Graham's law, where the rate is going to be proportional to the inverse of the square root of the molar mass. Interesting equation. How will we use these? So keep thinking about this. We'll relate the rate of one gas to the rate of the second gas as the square root of the ratio of their molar masses as shown in this equation on this slide. So the process where the gas escapes from one compartment to another by passing through a small opening is called effusion. And their rates of diffusion are going to be inversely proportional to the square roots of the molar masses. And this final equation is the way we're going to end up using it. All right, so ready to pull out your math skills. So think about diffusion as being a little bit differently. Here we have two different samples of solutions. They will have their bottles open. And as we notice that there's vapors collecting above one of the bottles. And so the gases are diffusing out of each of the containers separately, but apparently they're mixing as the gas vapors are gathering in the air above these two bottles. Now, there's random motion of the gas, which is what's represented on the left here. Each gas moves randomly, but when one gas comes in contact with the other gas, a vapor or a cloud is being formed. Well, why is that? Well, you probably can't read the label carefully, so let's label it better for you. That's ammonia, ammonium hydroxide, basically. And so the gas that's escaping is the ammonia, not the hydroxide version of it. The hydroxide version is what you get when you put it in water. The other container there is hydrochloric acid, and it has a larger molar mass. So the molar mass is going to be related to the rates of diffusion. And it's demonstrated by where the cloud is being formed, because if you react ammonia with HCl, the resulting product is ammonium chloride, which forms in the air over the two bottles. But notice where it's closer. It's closer to the HCl bottle because the HCl is not moving as fast. Its rate is going to be slower because it's a heavier gas that's escaping from that bottle. And so more of the ammonia has moved farther than the HCl has moved, so the cloud is primarily over the HCl, or closer to the HCl bottle. Okay, now we're going to use this law and do some calculations. You heard it coming. And so bromine is a gas. If you let it warm up, there will be vapors, and it has the molar mass shown here. Effuses half as fast as one of the noble gases. So how in the world do we set up this calculation? So the rate of one gas is related to the rate of the second gas. And its ratio is going to be the square root of the mass of gas 2 divided by the gas of mass 1. So to make this easier, let's call bromine gas 2. And the one we want to determine is going to be gas 1. So which one? That will be gas 1. The rate of the bromine is 1/2. So the rate of gas number 1 is the one we want to find, is half as much for the bromine. And so you put 1/2 down here. It's going to be equal to the molar mass of the bromine, 159.8, divided by the mass of the other gas that we still need to figure out. So the rate of the bromine is 1/2 of the gas of the other gas. Okay, so the term I have on the left looks a little funny. And so essentially, 2 is what we get when we simplify this fraction in the bottom half of, in the denominator of that fraction. 2 is going to be equal to the square root of those two values. So let's not write the square root, let's square it. And it's going to be 159.8 over mass 1. And so we can flip this around. 2 squared is clearly 4. So mass 1 is going to be 159.8 divided by 4. And guess what? That should come out to be a number that looks like one of these masses shown here. My calculation gives me an answer of 39.95. Well, that's pretty much right on for argon, isn't it? Now, does this answer make sense to us? Again, molar mass should be grams per mole. The way these are set up, that's always what you're going to expect. Does it make sense? Bromine is a higher molar mass. It's got a, well, relatively high compared to this list. And the gas, it's going to be moving slower than a gas of a lesser mass. And so it can't be anything large like the radon. Probably not so different from xenon. So it's going to have to be something smaller. So we know that it has to be something smaller, but the actual one that corresponds here is best determined by an actual calculation rather than trying to speculate it in your own thinking. Hopefully that makes some sense. Okay, so let's try one more. I'm sure you're going to be excited to work with square roots, but if we work them out carefully, we'll be fine. Let's find out that there's a weird compound with nickel forming a gaseous compound, and it's got carbon, oxygen, carbon monoxide kind of looking groups in it. And we don't know how many of them there are, but it's going to be with the nickel, and it turns out it's a gas. So we want to determine how many of those carbon oxygen groups are on the nickel, given that under the same conditions, methane effuses 3 times faster, 3.3 times faster than this unknown nickel compound. All right, there's Graham's law laid out for us, and let's decide what rate 1 and rate 2 are going to be and how we'll use it. So rate 1 is going to be for the methane. Let's call it methane gas 1. It's 3.3 times as much as rate 2. And the molar mass of methane, well, that's not so tricky. It's 16 grams per mole. Hooray. And how do we use it? So the mass of gas 2 is rate 1 divided by rate 2 squared times mass 1, molar mass 1. And put in some values, 3.3. In other words, put in R1 is going to be 3.3 times R2, and that means R2 cancels out. 3.3 squared times 16 gives you 174 as the molar mass. So given that, how do we determine how many carbonyl CO groups are on this nickel compound? Well, think about it. The molar mass of nickel is 58.7, and so only part of that 174 is the nickel, the nickel. So take the 58.7 and subtract it from the 174, and that tells you you have 115.5 grams remaining in the molecular weight that corresponds to the CO group. That the CO group is the 28. In other words, carbon is 12 and 16 for oxygen. So how many of those 28 molar mass groups goes into 115? And it's not exactly completely accurate, but it's close, and we should get a number here. And the number of 28s that goes into 115 is about 4. So it's essentially a little bit extra. But remember, these are calculations that get us close because you're measuring rates that are not given with too many sig figs and not too many sig figs on our molar mass, but at least it's accurate for methane. So 2 sig fig answer, 4.1, yeah, pretty close to 4. So apparently there's 4 carbonyl groups in that nickel compound. All right, here's another example. Gases effusing through a tiny hole. Let's put oxygen and hydrogen gas in front of us today. And apparently you've got 2 times 10 to the minus 2 moles of hydrogen effusing per 1 hour in a little tiny hole. How much oxygen effuses through the same hole in the same amount of time. So how much hydrogen per hour, that would be a rate. So the rate of hydrogen is going to be 2 times 10 to the minus 2 moles per hour. We're going to come up with how much in the same amount of time, so it's the number of moles that we're looking for. And so we want to know the rate for the oxygen. How are we going to do this? So we're going back to the Graham's law of effusion, if we remember how that looks. So the rate of the oxygen is the one we want to know, is going to be determined as a ratio to the rate of the hydrogen, equals the square root of the ratio of their molar, the inverses of their molar masses. So the mass of the hydrogen divided by the mass of the oxygen. Put some numbers in. Mass of hydrogen, well, last I checked, is pretty close to 2.02 grams per mole. Hooray. For oxygen, it's right about 32, close enough for all of our purposes. We'll get a reasonable answer, and this is multiple choice, so we know we'll be all right. And then we have a number that we haven't put in yet. So we're going to put a number in here. The rate of the oxygen is going to be divided by the rate of the hydrogen, which is 2 times 10 to the minus 2. I know I wrote that small. Equals the square root of those other values. So let's just square this instead of writing the square root again. 2.02 divided by 32, well, that's about 1/16, isn't it? And so we'll just call it 1/16. For close enough purposes, will get us right in this one. And so in order to get this equation worked out, what are we going to have to do? So we have the rate of oxygen squared is going to be 2 times 10 to the minus 2 squared. Squared, well, how does that work out? That changes things, doesn't it? Let's regroup. I did this a funny way. So instead of doing this the hard way, let's make sure we set it up correctly. Some of these you have to pay attention and make sure you haven't set it up funny. I'm going to do it the other way around because the numbers come out better. So let's do the rate of the hydrogen on top. Makes it easier to work with. The rate of the oxygen below, so that's our 2 point whatever times 10 to the minus 2 over the rate of the oxygen. Just be patient, we'll see how this works. Is going to be the square root of the mass of the oxygen, it's a bigger number now, 32 over the 2, and we know what we can do with that. 32 over 2 is 16. The square root of 16 is 4, so let's stop making these complicated. So the rate of the oxygen can be related to the 4 and the 2 times 10 to the minus 2. So the rate of the oxygen now, if we multiply both sides by the rate of the oxygen, let's put it over here, is going to be 2 times 10 to the minus 2 divided by 4. Half of that, And then we might be going in the right direction. And we have 5 times 10 to the minus 3, in other words, half as much. 5 times 10 to the minus 3 is the rate for the oxygen. Does this make sense? Is the oxygen going to effuse more slowly? Yes, it's a heavier gas, and there's our answer. Sorry for taking you on a detour there, but it's a good exercise in realizing that sometimes we set things up in a fashion that doesn't feel convenient, and so there are times to back up and start over and try again. But be very careful with your labels on your parts in this equation, because you've got to have the reciprocal of the molar mass in your square root lining up correctly with your rates on the left side. Alrighty, good luck with these. These are always challenging. Be careful to write things out carefully, in detail as you work your problems. And we'll see you in class. Ask lots more questions if these are not making sense to you.